Okay, so yeah, if you want to talk about something other than this, that's fine. Also, this is an open session, so we are actually trying to do exactly what Johannes did, which is talk about things you ran into with automation and how you dealt with it, or how what you would like in a wish list and so on. So in this, I'm going to present my own peculiar view of certain automated reasoning procedures. Okay, this is not at all that standard or anything like that, but it should be. Okay, so that's the kind of and when you're solving a problem, there are two approaches. You either reduce your problem to something that you or someone else has already solved before, or you perform a series of steps of inference to reduce the original problem to a solved form. And then either you in the solved form you can see that there is no solution, or you should be able to read off the solution. Okay, those are the ways of solving problems. So I'll be talking mostly about this latter way of doing things. And so there is a kind of form in which you can think about algorithms of this latter class. And the main thing is that this, when you do it, decomposes into having an algorithm consists of these three parts. One is just the inference steps. That is, you get a bunch of rules that you can apply in any order whatsoever, and it would lead you to a solution. The second is the strategy. Perhaps there's a better order for applying things than others, and so you try and follow that strategy. And anything will give you the solution, but perhaps the strategy will give you a more efficient path to the solution. And then you want the most efficient way of actually implementing the strategy. So given the strategy, you index things suitably. Okay, so these are the three parts to how you solve the problem. I'll only be talking about the first part, but you'll see implicit in this that there are strategies and indexing mechanisms and so on. Okay, and this is not just for inference algorithms. You can solve any problem this way. I mean, all computing is inference. Okay, so just some preliminaries. You probably know all this, but I'm just trying to make sure that we're going to be talking about a signature. A signature has some function symbols and predicate symbols. They come with their own addities. Equality is considered to be given. You don't put it into the sigma. Okay, then you have a sigma term. Okay, which is going to be basically either a variable or an n-ary function symbol. N is possibly 0 applied to n smaller terms. And so if you have an infix, then you could use infix or that, but that's a 2-ary function symbol. And then a sigma literal is going to be an n-ary predicate symbol applied to n sigma terms. Okay, so that's the idea. Okay, so you can have, for example, x plus y is equal to x plus 0 is equal to x, or 0 less than x. Those are all sigma literals. Okay, and so it could also be a negation of these. Okay, so 0 is not less than x is also a literal. So a constraint I'll interpret as a conjunction of these. So I'll just give you a set of literals, and constraint is a conjunction of these. A clause is going to be explicitly a disjunction of literals. By the way, I quickly ran out of letters of the alphabet, so I might be reusing some of the meta variables along in different ways. But roughly, this is so you have a variable, you have a term, you have an atom, you have a literal, you have a constraint, you have a clause. Okay, then you can take the free variables in the thing. So vars will just return the free variables in one of these, a term, a literal, a formula, constraint, and so on. And one of the weird things I do is that when I have a sigma structure M, normally M would give you meanings to the function and predicate symbols. Okay, so there'll be some domain absolute value M with respect to which you take the meanings of the function and predicate symbols. But I throw in the variables as well into that. Okay, so I assume that there's a mapping to the variables. And if you want a different one, just change what's in there to the one you want. Okay, but by default, the variables will also be mapped. So then you can say that M is a model for A if the evaluation of A under M, given that it already has the variables as well, is true. So that's the idea. And it's satisfiable basically if there is some model for it. Okay, So, for example, x equals y might be satisfiable, but x not equal to, what does this say? I guess that must be x not equal to x is not. Okay. And then A and B, this is the most important concept here. A and B are equisatisfiable if A is satisfiable, if then B is satisfiable. Okay, and all your problem solving steps go in equisatisfiable moves. Okay, because you don't want to lose any solutions. Okay, nor do you want to create any new ones that weren't solutions for the original. So that's why you want to move in equisatisfiable steps. And although equivalence implies equisatisfiability, it's not the same. Okay? So equisatisfiability is a different notion because there can be variables in A that don't occur in B and vice versa. So you may not be able to prove the equivalence, but you're making equisatisfiable moves. Okay. So then what are the inference problems? So the typical inference problems will be with respect to some theory, T out there, okay? The word problem will be just, find the validity of an atom. Is that atom valid in this theory? The uniform word problem is that, if you're given some, context gamma of sigma atoms, is P entailed by those? Is this P entailed by the conjunction of the gamma? It's the uniform word problem. And then the causal validity problem is, given, I guess, a sigma clause. I'm misusing K now, but is it a valid clause? The quantifier-free validity is going to be, I don't know what that is, but if is it the case that a quantifier-free formula A is valid in the theory? So it could be, so all of those could be turned into quantifier-free validity, for instance. And then quantifier elimination is, can you actually reduce any formula to a quantifier-free equivalent form? That's the quantifier elimination. And then interpolation is that if you have a set of formulas that is jointly unsatisfiable, then can you find an interpolant A in the intersection of the languages of the gamma and the delta, such that A is entailed by gamma and A together with delta is unsatisfiable. Okay, so that means that, for example, if say I don't know, George speaks French and English, and I speak maybe English and Hindi, okay, and we somehow disagree on something, then there's probably a statement in English that we disagree on. Okay, so that's the idea. Okay, so in the intersection of the languages that we speak. So so what is an inference algorithm? We're getting to that now. Okay, so it starts with an inference structure. So an inference structure is this quadruple which consists of an inference state, whatever it is, it's some abstract state. An inference relation, whatever it is, again, it's an abstract relation, it's a reduction relation. This lambda is the thing that takes this abstract inference state and turns it into a formula in your signature. And then there's a model extractor that takes the canonical form that you have, the solved form, and turns it into a model. Okay, this is the thing that is able to read off a model from a canonical representation. And the structure has to satisfy three conditions. One is that it has to be conservative, so every reduction step basically must ensure that psi and psi prime are equisatisfiable. Okay, that is, the corresponding interpretations are equisatisfiable. It has to be well-founded. There can't be any infinite sequences of reductions possible. And that if you do hit an irreducible, that is, when you actually stop, you hit something that you can no longer apply an inference step to. It's no longer reducible. This is the, again, the next important thing. Okay, it has to be manifestly unsatisfiable. It has to be bottom, or it has to be in this canonical form, that is where you can read off the solution. Okay, so it's like in this row echelon form and things like that. So it should be in a form where you can read off the assignment M that satisfies it. So, any questions about this? This is.
You could also get stuck, right? And then you don't know.
That shouldn't happen, is the idea. That the condition that canonizing states is that you should never be stuck in a state that isn't manifestly bottom or isn't satisfiable.
In practice, it might often happen like with higher order unification. You can either find find a solution,
Correct, yeah,
or
yeah,
it's
yeah. So
inconsistent
there are
with-
variants of this where you can go on forever. Okay, and so those are semi-inference algorithms. Okay, so the idea there is that if it's bottom, you'll stop at some point and you'll return bottom. But the model might be infinite, and you have to look at the infinite sequence in order to construct the model. And that happens, for example, first order resolution is an example of this. Okay. But this is just for decision procedures. It's for things that actually converge with one answer or the other. So what you said shouldn't happen. You shouldn't be in this twilight zone where you're in the state that you don't know is it could be satisfiable, it could be unsatisfiable, but it's irreducible. Right. So this actually gives you a template for actually proving the correctness of these algorithms as well. You just write down the inference rules, you check these three things, and you know that it's a good algorithm. Okay. And also, in some cases, you'll have things that are strongly conservative. That is, when you get this canonizing state, the model that you construct for it is a model for the original thing that you started with, the input state that you were given. Okay, so you can map it back. And many of the procedures we have are actually of this. They're strongly conservative. Okay, so then an inference algorithm is actually going to be something that generates these inference structures. So it's going to be given in terms of inference rules. So an inference rule is one where anytime you can it's a rule for taking a psi to a psi prime such that this reduction relation holds. Okay. So let's look at one simple example of this. This is ordered resolution. So here the input consists of a set of ordered clauses, and the idea is that you can have some say P is less than not Q is less than what's that?
Also Q should be Q somewhere.
So let's see.
The first thing is a Q.
Yeah, I think that's a Q. Yeah. So Q is less than not Q is less than P is less than not P. Okay. So that's the ordering. And then you have two. So another important point out here is that clauses containing both P and not P. That is P dot 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 or not P. Those are tautologies. Those don't contribute any information to the satisfiability problem, since those are just true. So you can just drop them. Okay, they're not constrain your solution in any way. So you drop tautologies from the input. So you're left with non-tautologies, and then what you do in each step is you take a clause of the form P or gamma 1 and not P or gamma 2, these two clauses, and you resolve them to get gamma 1 or gamma 2 as a new clause. That is, you add it to the other clauses. Okay, but you have to make sure that gamma 1 or gamma 2 is not tautological, because that could happen. I mean, there might be a Q here or a not Q there. So in that situation, you don't generate it. And then finally, the contradiction rule is that if you have a unit clause P and a unit clause not P, you derive bottom from it. That's when it's kind of manifestly unsatisfiable. Okay. So that's it. I mean, when these rules no longer apply, that is, you can't generate a new clause anymore with any of these, then you know that it's irreducible form. So here's an example. So you're given the input not P or not Q or R, not P or Q, P or R, not R. And that notation out there is just the label I'm going to use for that set of clauses. I'm just going to say, just call that K naught. Okay. Because I don't want to repeat the set of clauses over and over. So just call that K naught. Okay. So the first thing you do is you resolve not P versus that P or Q, not P or not Q or R versus P or R. And you get the clause not Q or R. Right? So then you can resolve not P or Q with P or R. Okay, these two can, and you get Q or R. Then you can resolve, then you don't have no further resolution steps on P anymore. Okay, so you're not going to get new ones, so you do the Q. Okay, so you do not Q or R with Q or R, you get R, and then R with the not R or there gets bottom. Right? So this is, you've paid attention to the ordering on this. You always resolved only on the maximal literal. And this should look very suspicious to you. I mean, that you're somehow only resolving on the maximal literal and it's good enough. Okay, that you don't lose any proofs when you do that. Okay, is it suspicious or not? that you can just resolve on the maximal literals? I mean, it does, I mean, it looks on the surface of it that you might miss some resolution steps, right? When you do this. But it turns out, no, I mean, that this is good enough. And this kind of thing is where you get a lot of efficiency. So, Another thing to keep in mind is if I drop that not R clause out there, then I would reach a state where, you would basically have all these clauses, R, Q or R, not Q or R, and those clauses, except the not R. And I can give it a truth assignment. That is, given the state, I can map R to true, and given that R is mapped to true, that's true. Okay, that's true. Okay, and that one is true as well. Okay, and this is true. So the only clause you're left with is not P or Q. Okay, and so I can make, for example, Q false and P false, and not P or Q would come out true. Okay, so I can give it an assignment. Okay, so why is this progressive, conservative, and canonizing? So it's conservative because when you add this new clause, okay, it's just as satisfiable as the input. That is, if these two are satisfiable, okay. So clearly, in any satisfying assignment, one of P or not P must be assigned true. Okay, if that's the case, if P is assigned true, then gamma 2 must be satisfied. And so gamma 2 is satisfied in that as well. And so that's also satisfied in that model. If P is assigned false, then gamma 1 must be satisfiable, and so gamma 1 is there also. So any model of the original set of clauses is also a model of this. And conversely, it's easy because it's a subset. Okay? Any model of the thing below the line is clearly going to be a model of the thing above the line because it's a superset of the things above the line. It's progressive because there's a bound to the number of clauses you can generate. Okay? So you'll eventually generate all the clauses you can generate, and you'll be done. The most interesting thing here is why it's canonizing. Okay, why is it that when you can no longer apply a resolution step, that you can read off a model from it? Okay? And this is a recipe for reading off a model. So start with basically now you've got this closed set of clauses. It's not bottom. And then you say, start with the empty truth assignment. In each step, you're going to basically give the I plus 1th. If you have mi, you're going to give the I plus 1th literal a truth value. You're going to give it a truth value v. If and only if there's some clause of the form pi plus 1 gamma in this irreducible state k, okay, such that mi falsifies everything there. So remember, those are all in smaller literals. So mi will give a truth value to that, a definite truth value. So if it falsifies that, then you're forced to make this one true. Okay. So why is that okay? So how do I know that by making this true, that there isn't some other clause also in pi plus 1, that pi plus 1 is a maximal literal? How do you know that's not going to be it has not pi plus 1 on it. How do you know that's not going to be falsified?
Because then you wouldn't be in an irreducible state, right? You could.
Yeah, because then supposing you had a not pi plus 1 or delta, then you would have done that resolution. You would have had a gamma or delta in the smaller literals. And if mi falsified gamma, it would surely have satisfied delta. Okay, so that a clause of that kind will always be satisfied. Right? So you can preserve this invariant basically. So every clause in P1 to Pi is going to be true in this model mi. So you always make sure of that as you extend the truth values. So you could have done unordered resolution as well. It's just not as efficient. I mean, it will also converge, and you can use the same argument model to get it, but it's just not such a smart thing to do because ordered resolution works. Okay, so take union find. I mean, union find actually is often presented just as a regular algorithm, but it's actually an inference algorithm. Okay, and again, I'll give you a funny version of it. So here you're given some input equalities, and you have this find structure. The find structure is always going to be idempotent. That is, if you take the find of a find, it'll always give you the find itself. Okay, so what you do is you orient the equalities. You orient y equals x as x equals y if x is greater than y in the ordering. And so you can either start with a fixed ordering, or you can make up an ordering as you go along. Either one is okay. You probably want to do the latter for reasons I'll tell you. So these are the rules. So you have G is going to be a set of equalities and disequalities. F is the find structure. So if you have x equals y in G as an input equality, then get the find of x and get the find of y. Okay, and if they're equal, then do nothing, just drop it. If they're not equal, then take the oriented form of those canonical forms. Okay, take the oriented form of those and make that f prime and compose that with f. So what it means to compose f prime with f is that you add this new equality and apply it to every right-hand side in f. So every right-hand side in f will have rewritten the left-hand side to the right-hand side. Okay, so that's what it means. So then finally, if you have a disequality such that the two finds are equal, then that's clearly a contradiction and it's false. So that's union find as an inference system. So you're just processing the input, building up a find structure, and just looking up things in there. And when you actually get a new equality, you merge the two equivalence classes. And the typical smart thing to do is you orient it so that you always I guess orient the heavier equivalence class to the representative of the heavier equivalence class points to the lighter equivalence class in terms of the cardinality. Okay, so that's what gives you this inverse of Ackermann function complexity. So is all this making any sense? I mean, the idea, we've seen these two inference systems so far. So you can also compute normal forms this way. So this is the SATand conversion to CNF. So basically, if you see a conjunction of two literals, okay, so these have to be basically P or not P types of things. If you see the conjunction of two literals, you basically add to the clause set. You add a new variable x, and then x implies L1, x implies L2, and L1 and L2 implies x. Okay, so that's what because it's an AND. Okay, so you're replacing that. If it's an OR, it's the other way around. So L1 implies x, L2 implies x, x implies L1 or L2. That's the OR. And finally, if you just have sorry, that's a mistake. If you just have a literal, the literal moves over to k. Okay, so that should become L comma k. Okay, so that's a mistake right there. Okay, so that gives you this conversion. So basically out there, you can replace this with R. So not P and Q, you can replace with R. And then this OR you replace with S. And then you return not S as the CNF. Okay. And again, you can see that that's progressive, conservative, canonizing, and so on. It's just introducing new variable names. Okay, so the next thing we'll look at is SAT solving with what's called CDCL. So that's conflict-directed clause learning SAT solving. So this gets a little hairy as an inference system, but I'll try and walk you through it. If you have questions, we can slow it down. So we're going to take a bunch of clauses in this conjunctive normal form. Okay, like for example, P or Q, not P or not and not Q, okay, and see if there's a satisfying assignment. And the way you're going to do it is by essentially guessing certain truth values. You're going to guess that way. Well, maybe I'll make P false. Okay, and you're going to propagate other truth values. Like if I make P false, I'm forced to make Q true. Okay, so that propagates truth values. So M will consist of this partial assignment with guessed and propagated truth values. Okay. So each guess will move you up a level in your partial assignment. So the levels are basically the number of guesses you have. And the implied literals are at a certain level. So if you got, like, for example, P at level 3, then, false at level 3, then Q is propagated at level 3 as well. Okay. You kind of maintain for any propagated, an implied literal, you maintain the reason that you propagated it. So for example, if you make Q true, you say I made it true because of P or Q. Okay, that's the reason that it became true. Okay. So that becomes the explanation. And then if M detects a conflict, that is, you made these guesses, and finally there's a clause that's falsified by the assignment that you have. Okay. what you do with that conflict clause is you analyze it. You kind of backtrack through the explanations until you kind of reach a certain nice conflict clause, which I'll get to, and that's what this analysis step does. So that nice conflict clause becomes a new kind of lemma. It's a thing that's implied by the input. So you add it, and so what you do then is back jump to a point where you can then use that as a clause for getting an implied literal. So you back jump to a level smaller than the current level h, and then you can continue the search from there. And then if you reach a point where there's no way to extend it and no conflict is detected, then what you do is there are no implied literals, no conflicts. You make another guess and continue the search until all the clauses are satisfied, or you hit a conflict at level 0. So a conflict at level 0, things at level 0 are things that are absolutely the literals implied by the input. So if you have a conflict at level 0, if a clause is falsified, then it means that it's genuinely false. That is the negation of that clause is implied by the input, so it's unsatisfiable. So these are the 4 inference rules. So the first one is this thing that propagates the truth value. So it says basically that to m, I'm going to add the literal L with explanation gamma. Okay, if gamma is of the form L or gamma prime, and m falsifies gamma prime. Okay, basically, m makes everything in gamma prime false. Okay, then I am forced to make L true, so I'll make L true with explanation gamma. Select says basically it's a situation where I can no longer propagate anything. So what I do is I add a new literal L with an empty explanation, and I bump the level up h plus 1. Okay, so to the partial assignment I add this new guess, and it should be the case that it's neither implied nor refuted by m. So a conflict is one where you have a clause gamma in this K union C. C is the set of conflict clauses, things you've learned. Okay, then that is falsified by M. And if the conflict occurs at level 0, you're done. Okay, this is unsatisfiable. Back jump is the kind of most complicated thing. This is where you're getting the huge benefit from this conflict-directed clause learning. So in this case, you've got a conflict. It's at level h plus 1. So it's at some level that's not 0. Okay, and what you do is that you take that gamma and you analyze it with respect to the current state. So whatever the psi is, you analyze it. You get a new level and a new conflict clause gamma prime. And so what you do is you back jump to that level. So you go back to h prime, the smaller level, and you add this literal L as a new thing at that level. So you always learn a new literal when you back jump, and then you add gamma prime to the set of conflict clauses. So that's it. So it's a simple kind of 4-part state in which you keep learning new conflict clauses. The K stays the same; it never changes. The M can grow and shrink as you make guesses, as you get implied literals, it grows. As you back jump, it shrinks. Okay. So the analyze step, what it does is if you're given this clause L or gamma, and essentially everything in gamma is below level H, then what you do is you return the maximum level in gamma. So you return the maximum level of a literal in gamma, and you return L or gamma as the conflict clause. So at that point you're done, and L is the literal you can actually add out there. So L is that literal that you can add. Okay. So what this says is that at the literal L becomes implied at the level of gamma. At level of gamma, everything in gamma is going to be falsified. So L is going to be implied, so I can add that. Otherwise, if you don't have that situation, then you pick basically the kind of maximal literal, and you take its explanation gamma prime, and you essentially resolve it out. So you resolve L against that, so that's going to be, remember it's falsified, so it's got to be in the form complement of L. So you resolve it, you get gamma prime or gamma, and then you continue the search until you reach that situation. And this will terminate because eventually you'll hit the decision literal if nothing else goes wrong. At the level H, you'll hit the decision literal, and that will be the unique literal at level H. So you'll always hit this condition eventually.
How do you compute the level of a literal?
It's the, in M, you know the level at which it was either implied or guessed.
Well, you only record this gamma. With a literal, you record gamma.
So the level of gamma is the maximum level of a literal in gamma. And remember, gamma is falsified by M. So every literal in gamma has its opposite as an assignment in M.
Should you add some more information when you add something to M? I mean, it doesn't record it.
Oh yeah. So you need to record its level. Yeah, you need to maintain the level of that. So what I've done is actually that semicolon there is kind of marking the level. So if you add something without the semicolon, that's just a comma. It stays at the same level.
Okay.
The semicolon is like a bump the level up by 1. Okay. So that's the kind of trick out there to tell you what level you're at in this. But you're right. Yeah, you need to keep track of the level at which a literal was either implied or guessed. Okay, so let's look at an example of this. The example is just those formulas. So we'll do the search in a very bad kind of order, but let's see how it goes. So first, for some reason, we decide that so there's no unit literals in there, right? There's not a single unit literal. So at level 0, I'm not going to get any implied assignments, right? So what I'll do is I'll just say, okay, at level 1, I'm going to guess that S is true. So if I make S true, do I get any implied literals? Okay, so that one out there, if I make S true, I just get that. I don't get a unique literal that's implied by it. And nothing else. If I make S true out there, nothing happens and so on, right? So I get no information out of making S true. Then I make R true. So, this is the second level. At the second level, I make R true. So if I make R true, then this one, basically not Q, is going to be implied by this clause, right? Because if you make R true, that's false. I'm forced to make not Q true. So I add not Q with this not Q or not R. Okay. Now that I've added not Q, okay, then if I look for occurrences of Q out here, so for example, there, Q. So I've made not Q true, so Q is false. So I'm forced to make P true, so that P or Q shows up out there. Okay. But once you have that, you hit a conflict with not P or Q. Where is not P or Q? This one. Okay. You hit a conflict with that. Okay. And then what you can do is you can start analyzing that conflict. Basically, not P or Q resolves with the explanation for this, with P or Q, and you get Q out of it. Okay. So that's what will happen in the next. So when you analyze it, so you have that conflict, not P or Q. So you add the new clause Q out of that. Okay. So the Q is the new clause. And you can back jump all the way to level 0 because Q has nothing on the other side of it. So the level of gamma, the maximum level of gamma is 0. Okay. Because there's nothing there. So you back jump all the way to level 0 with Q. And that makes sense. After all, you resolve two input clauses with each other. You resolve P or Q with not P or Q. You got Q at level 0. That makes perfect sense.
I didn't understand why you got Q. How do you get Q exactly?
So P was implied was implied because of P or Q, right? Mm-hmm. And the conflict clause is not P or Q. The reason it was falsified was that you made every literal in it false. Okay. So clearly there must be, the opposite number of this lurking in the M. And I can resolve these two. When I resolve it, I get Q as the resolver.
Okay.
And then, so that means, that's a new conflict clause. Now, Q is a unique literal at level 2. It's the only literal in the clause at level 2. So I can back jump to the highest level of the rest of the clause. There is no rest of the clause, so that level is 0. So I can back jump all the way to 0. So that's what I did out there. Now, when I back jump, I have a unit clause out there. I can add Q with explanation Q. Okay, it's implied. Q is implied by the input. Okay, once I have Q, I can get P from P or not Q. Okay, so because that's falsified, I'm forced to make P true. Okay, so once I have P, I can get R from not P or R. Okay, because this is falsified, so R is supposed to be true. And that is a conflict with not Q or not R. Okay, not Q or not R is falsified by that assignment, and that's a conflict at level 0. So you're done. It's unsatisfiable, right? Okay, why is it correct? So this is the tricky thing out here. Okay. I mean, does it look straightforward? Does the procedure look straightforward, the CDCL thing? Is it clear what steps you need to take? That, in each step, you can either guess an assignment for a literal that is unassigned. You can, propagate an assignment as an implied assignment, or you can you have a conflict and you can back jump, and you analyze the conflict and you back jump. Those are the things. And if you have a conflict at level 0, you're done. So the progress is that every time it looks like you might be back jumping and growing and back jumping and growing infinitely, right? But that doesn't happen because the more assignments you have at the lower levels, it just accounts for way more than as many assignments that you want at higher levels. So you can think of it as currency. That each time you go up a level, okay, you can think of it as in whatever base you have. You're getting a $100 bill instead of a $10 bill instead of a $1 bill. Okay, so you're kind of going. You're getting more valuable assignments. So that's the reason that it progresses. That is, eventually, you cannot keep going. There's a limit to the kind of you can make all the assignments at level 0 and then you're done. Okay, that's the maximum you can do. That's the most money you can make on this. So it's conservative because if you just take what's in the M0 part, okay, together with K and C, that part of the state is equisatisfiable. Because everything you put in M0 is implied by K and C. Everything you put in C is implied by the previous K and C. Okay, so everything that you add is actually implied for this M0 K union C. Okay, so that's why this is the part of it that is actually equisatisfiable. So this thing is actually the lambda that you extract. All the other stuff is just bookkeeping. Okay, all the levels and the partial assignments beyond M0 is just bookkeeping. So this is the actual lambda. Okay, and canonicity, it's clear that if you're hit a irreducible non-bottom state where no more assignments can be made, there are no conflicts and so on, you have a total assignment. Okay, so if you have a total assignment and there are no conflicts, it must be because every clause is satisfied. So that's the way you reason about these infant steps. That is, you've got to show progress, conservation, canonicity.
I guess the progress could be a bit simpler if you use ordinal measures, or just
you can do it. I mean, actually, you could treat that as a lexicographic thing, for instance, and it is kind of becoming, but you don't need to. Actually, you don't need a lexicographic measure for it. So I'll skip the implementation notes. I mean, basically, when you go to implement it, what you find is that you got to do the indexing carefully. So, one of the key things you need is that you need to be able to propagate the consequences of new assignments quickly. Okay, so you need to find implied literals. So there's a trick called the 2-watched literal trick. Okay, that you basically in the 2 watched literals in a clause. Okay, both of them are either unassigned or one is assigned true. Okay, so that way, if it's assigned true, you ignore it. If both, every time one of the 2 watched literals gets assigned, you pick a new unassigned literal to make watched. If you can't find a new one, then you know that that's going to be an implied literal. So the other one is going to be the implied literal. So that makes it fast to actually propagate. So that's this trick out here. There's a selection heuristic. What do you pick? Which literal do you pick to kind of make a guess on, and what do you guess? What truth value do you guess for it? Okay, so you pick the ones that have been most active in recent conflicts. That is this heuristic, and the guess that you make for it is typically the last one that you guess for it, the last value it had. So that keeps the search space. It basically finishes one part of the search space before moving on to another. So these are very effective. And then, frequent restarts are really good. So you can just keep restarting the algorithm. In fact, you can just, as soon as you learn a new clause, you can restart. Any new information you have, you can restart. Okay, so it turns out to be really good because in the initial thing, you'll just be learning a lot of stuff. And once you have that, the search proceeds much better. So, and there are a number of other kind of pre-processing and in-processing things that happen as you pick up new clauses. You can clash them with other clauses. You can get certain implied information out of them and so on. Okay. So now let's look at something called superposition. So this is again a really weird thing. So we're just dealing with clauses that involve equalities between variables. That's all. Okay. Just equalities and disequalities between variables is all you have in your clauses. And you have to find out whether a given set of input clauses is satisfiable. So, in logic textbooks, they never treat this fragment with respect. I think this is, the most important fragment. This is where you step from propositional logic to saying, I'm going to look into the proposition and what I see is an equality. Okay, and it's just nothing else but an equality between two variables. So this actually, Schoenfeld just does mention it in passing. He calls them quasi-tautologies, things of this form. But it's really a nice fragment because you can learn, a lot of these ideas in the simple setting. So here you have, items of the form x equals y. There's an ordering of the variables. So you keep it in the form x equals y if x is greater than y. And so the literals also kind of get this lexicographic ordering on the variables. And so the clauses are maintained in decreasing order. And so the tautologies are deleted, and things like x equals x are also deleted, and any unit clauses of the form x not equals x. I mean, literals of the form x not equals x are deleted as well, because they're just false. Let's see, yeah, I mean, actually, clauses containing x equals x are deleted. Okay, that's the idea. So literals of the form x not equals x are deleted, and clauses containing x equals x are deleted. So, for instance, this might be an input: y equals z, x equals y, or x equals z, and x not equal y, or x not equal z. So, in the superposition inference, the idea then is that you have these rules. Okay, so the right rule, what it does is it takes a clause of this form. Again, I'm misusing all the letters, but you have x equals y and x equals z. Okay, so the right rule basically says, add y equals z to that, because this thing basically, on these two you can make y equals z under the context L and K. So, I mean, one way of reading clauses that I find helpful is you can think of anything like this as saying not L implies x equals y, not K implies x equals z. Okay, if not L implies that and not K implies this, then not L and not K implies y equals z. So that, as a reading, that's helpful. So the left rule now has the same kind of thing, but it has x not equal to y prime out there. Okay, x equals y or L, x not equal to y prime or k, you get y not equal to y prime from that, from L or k. So the EQ res basically says if you have something of the form x not equals x or L, you drop it. Okay, if it shows up in one of these things, you drop it, just as you did in the beginning. Factoring says that if you have x equals y or x equals z, then you basically add x equals z or y not equals z as a new clause, basically. And contradiction is when you end up with something in the form x not equals x. So let's look at an example. So the main things to remember are factoring. So x equals y or x equals z becomes x equals z or y not equal to z. And left, which is that x equals y or L with x not equals y prime or k becomes y not equal to y prime or L or k. Okay, so let's try and read this. So it's a little hard following these mechanical rules. So But what goes on out here is factoring out here can apply to, I guess, which one? X equals y or x equals z. When you factor that, you get x equals z or y not equal z. Correct? So this is factoring, remember. And so all you have is, you don't have an L, you have just this. So you get x equals z or y not equal z. So that's what you get out there. Okay. Then the left rule gives you this x not equals z or y not equals z. And the left rule basically, I think, takes those two. So it takes x equals y and x not equals z. And clashes those two, and then it ends up with x not equals z.
What was left rule doing again?
So left is x equals y, you're looking for, and x not equals y prime. So you're looking for two things of that form. So so x equals y out here, and x not equals z out here. Those two would clash. Okay. And what would you end up with? You would end up with y not equal to y prime and the rest, right? So that's y not equal to z. So this would be y not equal to z and the rest. So that is,
No, are we? I mean, we are.
and x not equals z.
Isn't it where gamma 1 is y percent and gamma 2?
Gamma 1 with, so y equals z with,
And gamma 2.
and this one, is it?
Yeah.
So you get, so y equals z and y not equals z. No, it shouldn't be that actually. You should always clash on the maximal one. This one,
Oh yeah, so it's the middle one on the, so it was the last one.
not equals z.
Oh, should be a Y.
I've checked it, I'm pretty sure it's correct. So
Oh,
You have to write more evidence in the rule name.
yeah, so yeah, that's example. Anyway, the point here is that if you apply these rules, and you end up with a contradiction because eventually you get the left with y not equals z and that clash. That's the left rule. You get z not equal to z, and that gives you bottom. And so the point here is that if you leave that out, you end up with an irreducible state. If you leave y equals z out, you end up with an irreducible state. And actually, the exact same reasoning you applied for resolution will give you an assignment. Okay, so you can essentially build up an assignment in stages, and in each stage you'll assign the i+1th variable a truth value depending on whether it's forced or not. Okay, so you'll pick the minimal clause of this form, okay, that is unassigned, and then you'll basically say I have to make i+1 equal to y in this because this is unassigned, and that is I'm forced to make that. And it's safe to do because the other rules make sure that the other clauses will be satisfied anyway. Okay, so that's the reasoning there. Okay, so the next thing is actually a kind of simpler problem than, in some ways, than superposition. But now you have terms. That is, your input has function symbols applied to n arguments. Okay, so you have f of a1 through an and so on. And you're asked to decide whether a given set of equalities and disequalities is unsatisfiable. Okay, so you're given this, you can be given, x is equal to y, but f of x is different from f of y. Okay. Is that satisfiable or unsatisfiable? X is equal to y, f of x is different from f of y.
Unsatisfied.
Unsatisfiable, yeah. So those are the kinds of things you have to detect with Converse closure. So
The functions are not injective.
they are just arbitrary functions in any function. So when you get to Skolem functions, actually they become injective, but these are not. So the state consists of these four things. The find is what you've seen before. We're also going to maintain the disequalities. We're going to process them into a disequality set. Okay. G is just the input. It's the input equalities. And U is going to be something that labels these compound terms. It's just going to pick a name for the compound terms and save it there. Okay. So that's what you're going to see. So this is actually very straightforward. So if you have some disequality where the find of x is equal to the find of y, then clearly that's a contradiction because that disequality is falsified. So if you have some input x equals y where the find of x is equal to find of y, then you drop it. Otherwise, if you have a thing where the finds aren't equal, you get the canonical forms, you orient them and compose them with f. Okay, so you maintain f in this idempotent form all the time. If you have a disequality where x is not equal to y, just add that to d. You can just throw that in d, nothing significant going on out there. So these two steps are interesting. So the first one says that if you already have a name for f of x1 through xn, that is when you have it normalized, if you already have a name for it, then just pick that name, just replace it with x. If you don't have a name for it, give it a fresh name and add x equals f of x1 through xn to u. Okay, so give it this new name. That's all. It's just making use of a variable to name a compound term like this. So then, if you the last rule is called propagate, and basically if you have a situation where you have x equals f of x1 through xn in u, y equals f of y1 through yn in u. And what happens is somehow the find has made them equal. So the find of xi is equal to the find of yi for each of those. Okay? But in the original finds they weren't equal. Then what you do is you take the representative of x and the representative of y and you orient it and you compose it with f. And you continue the search. Okay, so you're just making use of that find structure to the converse closure, and this propagate rule finds these opportunities for things where you have x is equal to f of x1 through xn, y is equal to f of y1 through yn. Now, the information that you were given, all the xi's and yi's match up. So you need to take the x and y and find their canonical representatives and add them to f. That's all this does. So I won't give you an example of it. So almost the last thing is this satisfiability modular theories. So I'm presenting a very naive version of it. So what happens that if in the CDCL inference, instead of just p's and q's, you have things like x is equal to y or 2x plus 3y is less than 18 and things like that. So you have some actual content in the atoms. What happens then to the algorithm? And all you need to do is you just keep all the other rules the same. Okay, there's a very naive way of doing it. You keep all the other rules the same. All you do is you add a theory back jump. And the theory back jump, instead of finding a propositional conflict, instead of finding a clause gamma that was falsified by M, what it does is it finds a gamma that is a theory consequence, okay, from the thing. So it's a gamma that is a consequence of the theory that actually contradicts M. So M would have said, supposing I made that true, for instance, and the theory will say, that can't happen. So, for instance, a good example is the one I just gave, where in M you happen to say x is equal to y, and you say f of x is different from f of y. Okay, then that theory, the previous theory we had should complain. It should say, no, that's not the case. And it should say why. It should give back a lemma saying it's because x equals y implies f of x is equal to f of y. That is, x not equal to y or f of x equals f of y. So it should generate that as the gamma. So essentially that's what gamma is. It's a theory consequence. It's a lemma that follows, like x not equal to y or f of x equals f of y. And it should basically be from the subset of literals in M. So the literals in L must all be false in M. And then you just analyze it as before, and you add the new literal out there. And in addition to kind of adding, back jumping to the kind of lower level of M and adding this new literal, you add the conflict clause to C, you add this new theory consequence, the gamma, to K as well. Okay, so you add the theory lemma to this as well. But the theory lemmas are always in terms of the literals that you were given. Okay, they're always disjunctions of literals from the input. Okay, so that's all the theory does. So, I mean, the reason this is naive is that this is not what actually happens. The decision procedure state is maintained continuously. That is, as you add a literal to M, you assert it to a theory state. Okay, and so that way the theory will tell you as soon as a conflict happens, it will say, oh, you can't make that true. There's a conflict, it will give you a lemma. The other thing the theory can do is it can say, oh, based on the literals you have, I can actually propagate some truth values. Okay, I know, for instance, that if you told me x is equal to y and y is equal to z, I know that you have the literal x is equal to z sitting out there. I can tell you that's true. Okay, so from it can propagate the consequences of information that's being given. So things like that can be added to this, but this is enough for completeness. So with this, you get complete theory reasoning. So you can take any quantifier-free formula, and it'll be able to tell you whether that's satisfiable or not. As long as you have a theory solver, as long as you can do this. Okay, then there are variations on this. You can do. You saw in CDCL, you're always making a kind of partial assignment. So there are lots of decision procedures that do that. So if you're doing difference logic, for instance, you keep an assignment. There's a version of simplex as well, where you keep a partial assignment, and then it's more or less just a kind of putative assignment. It's got no semantic value in the inference procedure. I mean, it's got no kind of inferential value in the procedure, but you can quickly rule out certain things from the semantics. So this is led to a class of procedures called MCSAT. And so, for instance, the idea in MCSAT is that just like CDCL makes Boolean assignments, MCSAT also makes non-Boolean assignments. It'll say, oh, let x get 2, and maybe that propagates to y gets 3. Okay, well, then let's guess that z gets 17, and so on. So you can keep adding to the trail that way with the kind of non-Boolean as well as Boolean assignments. And then when you hit a conflict, that is, you're no longer able to make an assignment to a variable, you can analyze what the source of that conflict is and learn something about the variables you've assigned. You learn new lemmas about the variables you've assigned. And that kind of forces you to revisit the assignments and make new ones. So this actually, Dejan and Leo have actually done a nonlinear arithmetic procedure along these lines as well. And it just works so much better than the kind of other stuff people have tried. So just this kind of guessing and finding a conflict is a kind of lazy thing to do. That's why it works so well. Okay? I mean, after all, if it's satisfiable, maybe your guess actually found the assignment. If it doesn't, it rules out vast swatches of the search space. Okay, the conflict rules it out. So it's actually quite an effective way to just kind of guess and retract from it. And this style, actually, we call our procedure CDSAT. So we have a combination version of this, where you can have individual conflict-directed theory solvers, and you can combine them into a conflict-directed combination solver. And the Boolean theory is one among them. That's all. It's just treated the same as all the other theories. So this actually, it gives you kind of a lazy way of doing the search. So you just kind of when you make an assignment, you're actually communicating a lot of information to the solvers. So this information would be hard to communicate otherwise. If I want to say, X is different from Y is different from Z. I can just say X gets 1, Y gets 2, Z gets 3, right? Saying that, saying X is not equal to Y, Y is not equal to Z, Z is not equal to X is a much more complicated thing to do. One is linear, the other is quadratic, right? So that's the advantage of this kind of conflict-driven solvers. And actually, there are many conflict-driven verification procedures also. If you heard of Bradley's algorithm, for instance, it's a way of actually finding inductive invariance, loop invariance. So that's also a conflict-driven procedure. So the question of modularity I brought up just a little bit when I talked about combination decision procedures, but you've probably you've heard of things like the Nelson-Oppen procedure. So Nelson-Oppen is a way of taking two theory solvers, each for a theory that's disjoint from the other, and combining them into a single theory solver. All they need to do is exchange information about equalities between variables that they share. Actually, another way to look at it is that you can just guess an arrangement on the shared variables. That is, you can say, just put the shared variables into an equivalence class, say all the ones in different equivalence classes are different, that's an arrangement. And then with that guess, you can say, do the two theory solvers agree that it's satisfiable? If it is, then you can get a joint satisfiability theorem. So as long as you have such an arrangement, if you've exhausted all the arrangements and they're always coming out unsatisfiable, then the whole thing is unsatisfiable. And then for special cases, there are simpler things you can do. You can just propagate implied equalities across the wall to the other theory, and you can get information out of it. So I was working on these kinds of things in the early 2000s, and Ganzinger, Harold, Bruce, and I actually worked out a very general framework for theory combinations where it's not necessarily disjoint. You can have non-disjoint things. That is, it's the same kind of thing like with George and I communicating in English. So it would be the same kind of thing. There is a theory sitting in the middle of us that both of us actually agree on. And we just kind of communicate across to each other in that shared theory. And if we are jointly satisfiable, if he's satisfied, or we write on the blackboard all the stuff that we need to make sure all the theories know about. So if each of us is satisfied with what's on the blackboard and our theory specific stuff, then if amalgamation can be used to combine the individual models into a joint model. Okay, so that's the thing you can do with this. It's quite a powerful thing. By the way, amalgamation is it's the nicest theorem in model theory. You can get all the other theorems as consequences of it. So this is interesting. I had more stuff, but one of the things that's missing here, actually, I thought I had the slides out here, is that you can take almost any textbook algorithm and turn it into an inference algorithm. Take sorting, for instance. Okay. So in sorting, the idea is to kind of make sure that you transform an array A into an array A prime into an array A double prime and so on. So that each one, if I could get the sorted version of that one would be the solution to the original array as well. And in order to go from A to A prime, all I do is I find an inversion. That is, I find an AI and an AJ where AI is greater than AJ, but I is less than J. And I flip it. I just flip those two. And you can do that in any order you want. Okay, and it'll come up with a sorted result. That is, at some point you just won't be able to do any more flips. And so at that point, it's got to be sorted. Right? So that's a way to do sorting if you want. The only thing you can, you might want to do on top of that is say, oh, I need a strategy for doing it. I need a good way of indexing it and so on. And then you come up with things like bubble and merge and different strategies for actually finding the inversions. Okay. So that's the like, for example, in insertion sort, you'll always maintain a prefix that has no inversions in it. Okay, the inversions will always be between the prefix and something on the other side of the prefix. Okay, so that gives you a strategy again for how to index the inversion. Because the naive thing I gave you, you'll have a tough time finding inversions. It's not so well indexed. Okay. Same thing you can do with Dijkstra's algorithm. In fact, I think any algorithm you'll find in a textbook, you can turn into this inference algorithm form. And, I mean, this is true for distributed algorithms as well. There's always inference going on in each step. And for me, I find this actually, more helpful than, things that are like models of calculation, things like Turing machines or automata, things like that, soulless things. Because the idea of the algorithm is actually, I think, better captured by the inference steps. And then there's this bookkeeping of strategy and indexing and so on. But if I can get the kind of idea that, oh, these are the steps I need to do, I can do them in any order and I'll get a solution, that's good enough. And, that's why I present things in this weird form. It's not, you could have understood the algorithms individually without this kind of presentation, but I try to give it so that you can see the uniformity of it across all these different algorithms. There are many topics I did not cover in this. I haven't done interpolation, I haven't done quantifier elimination, all these things, but I think these are, talk about it more. I'd like volunteers for future sessions as well. So if some of you are staying here and would like to talk about proof automation issues, we'd definitely want to learn about that, because I think the way Johannes presented it, it's really nice, because these are the kind of bottlenecks that will keep not just mathematicians from using our stuff. Maybe they would, but students wouldn't use it. We want things that are automation that is straightforward and easy enough and takes care of a lot of teaching that even students could use. Whether these kinds of things, you probably know SATand SMT solvers are widely popular.
So I had a question. SMT, where you need entailment should be decidable in the. If you have a list of hypotheses, does the conclusion follow? I mean, you have this.
That's all I need. Yeah. The red thing is all you need.
This must be decidable.
Yeah. That's right. So this is what I call the causal validity problem for that theory. The causal validity problem is
And about your general remark about algorithms, so this framework is basically analyzing an algorithm as a sequence of simple steps, right? So how about concurrency?
So you can, in this thing, basically, when you have the state, you can arrange the state so that certain inference, most of the inferences are monotone, because you could have done it in any order, you're just adding stuff. Okay? But you can arrange it so that certain inferences are independent, that they don't conflict with each other. If you do one, it doesn't rule out the possibility of doing the other, so you may as well just do them simultaneously. And then the theory combination I talked about, that is actually one where there's the shared blackboard you're communicating. That's kind of a concurrent algorithm as well. The theory is just every once in a while they look at the blackboard to see is there anything new out there. And if there is, they just continue to do their work. Otherwise, they can do their work independent of the other side, the other theory solvers. So that's an example of something like this concurrency. And I didn't talk about these semi-inference systems either, where you're not expecting to see the thing stop at some point. That is, either it says I can't continue any further, or the infinite sequence is what you can read off the model from. So if you do a sequence proof search, for instance, and you do it in a fair way, there'll always be one branch of the proof that diverges, and that is the model. So that's an example of a semi-inference system.
Are there concurrent implementations of SAT?
Yes.
You know?
Yeah. The Marijn Holzl will be speaking at the workshop, and everything is bigger in Texas. That's the title of the talk. So his stuff works in parallel, actually. I think like a 2,000 core machine or something grinding away on this stuff. And he generates proofs that are in the terabytes, and he checks them with a verified checker.
I think Tom Hells could generate petabytes if he exploited the nonlinear equations.
You probably could, yeah. So these are problems that are combinatorial problems. So what he looks at, like the Pythagorean triples problem and so on. So they are combinatorial problems. They're looking for objects satisfying some constraint and showing that there isn't such an object. So the proofs are really going to be huge in this. And then I think he's done a new one, which is even bigger. So he's actually working with Scott Aronson on trying to finish the Collatz conjecture. So, they're trying to do it in a style similar to the four-color theorem. They're trying to come up with certain configurations that cover all the possibilities, and showing that each one of those is got a kind of reduction there, termination argument. So apparently they have a competition where Marine runs the SAT solver and Scott Aronson does it by hand to see who gets there first. Yeah, and sometimes it's not necessarily the combination of these things. Sometimes you just want to use the theory solver independently. You want to use it in an interactive way. That is, you want to be able to make assertions to it and get a theory state built up, and then some of that theory state you can apply to a host of problems. Yeah, so I figured some of the people at the beginning part of this, I mean, the people in the latter half of the program will probably be familiar with this material, but I thought maybe the people in the front part of this might like to see what possibilities there are. There are actually a lot of interesting open problems in doing these things that, there are theories that you could look at. There are theories for which, we don't know whether there's a quantified elimination procedure or not. There's the problem of coming up with a modular way of actually, producing proofs and combining the proofs. For instance, how do you do that? How do you? There are actually papers on how you can take procedures that individually can generate interpolants and how you put them together to get an interpolant out of it. There's just lots of theories out there, and we don't know good ways of solving them. And also the techniques kind of scale very nicely. I mean, I talked about the congruence closure, for instance. From congruence closure, you can actually go to Knuth-Bendix completion. Here you have actually variable. You can think of congruence closure as the ground version of Knuth-Bendix completion, where you're not instantiating any variables. From that, you can go to solving the uniform word problem for commutative semigroups, and from there you can make the transition to Grosvenor bases. All of these are still kind of inference systems, okay? But they all just look a little more complicated than the previous one. But it's a very kind of smooth transition through these different inference systems. In 2003, four of us, so Harold was, Leonardo, Ashish, and I think. We taught a course at Stanford called Little Engines of Proof. And so if you look at the slides, you'll find a catalog of inference systems in there. So we did lots of proof systems, propositional things, approaches to SAT solving as well. It's like about 18 lectures on how. Another challenge here is actually to verify some of these things. By the way, once you present it in this form, you can see how easy it is to actually verify the thing. So this is why I don't actually have much sympathy for this, for tactics and things like that. It's a waste of time. Just verify the damn thing. It's a easy thing to do. And you can verify procedures that don't look great as tactics. With tactics, you're more or less in a certain straitjacket. Whereas if you just verify it, you need to.
You mean verify the proof trace or verify the whole procedure?
Whole procedure. Don't bother running this. Run a verified SAT solver, for instance. Don't run this trace checker.
But the way Marijn does it is
He runs a verified trace checker. I mean, the reason for that is that these are moving targets. He wants to keep changing it depending on what's going on, and so if he's changing it that often, it's hard to. I think we can imagine a time when it's possible to actually make sure that the proof is robust enough that it's able to fill in things for the change. That is, as you change it, it's either going to find a mistake or say no, the same proof more or less works. Like I told you, the guys in NASA have done these tasking theorem and things like that. They've done a verified nonlinear solver.
So I know that Marijn has this ACL2 verified proof checker.
Yeah.
I wonder, I think the Isabelle people have some like a verified solver, right?
Oh yeah, color.
So I wonder what's the speed
So we've done. I mean, I had a student do a verified SAT solver as well. It's a minor exercise, but you'll get a very poor speed out of it.
I mean, it depends. So Kava, for example, tries to have a speed in 1 or 2 orders of magnitude slower than millisat or something. Or
That's pretty good. So that's after extraction to ML.
yeah, it just runs in ML, and
Okay.
there's a lot of work to actually get to this point at all.
Yeah, and actually, by the time anyone makes that claim, it's probably the SAT solvers are moving very rapidly. So it's a tough thing to keep up with them. So they're constantly discovering new in processing and pre-processing moves and things like that. So
But I mean, that's a problem if you want to verify the algorithm and not the trace.
yeah.
I mean, if they produce if you just check the trace, you can concentrate on this one.
Yeah, but I think if you're doing the work properly, you can verify it as you kind of do these optimizations.
Well, you don't need to verify the strategies or any improvements are
But the
that
heuristics-
go down to strategy.
In fact,
sort of go-offs from the point of view of verification.
The trace checking is a massive pain for people doing these things because if it's a moving target, the trace is also getting messed up. And a lot of times you're doing things that actually you can't see the proof back in terms of the input because the input variables are gone. Okay, the input clauses are gone. They've all been simplified away. So the information is not there. And you should see the Z3 guys complaining about having to generate proofs. I mean, they just don't want to do it.
Well, we are the guys who are trying to force them to generate proofs, and they are the guys who are doing it and not doing it and doing it and not doing it.
Right.
There's been a TP support and it's gone again. And
Yeah, so they complain bitterly about being on their side of it. so I mean, like my colleague Bruno, who does Yikes too, says there's no way in hell I'm going to do that. It's just not worth my time. These things do have bugs in them. So Dayan is very good at actually finding bugs in Z3 and Yikes. He finds lots of bugs. So in Z3 at least, Yikes doesn't have that many. But he says these are all things which are mostly like corner cases. He just happens to run them because he's always in the corner. He says these are things that most people who are using them will never really see. There'll be something that was done kind of as a special case for something that wasn't used much by anybody, so it never got tested out. Actually, another thing that is kind of tough about these are benchmarks. I mean, you know, the benchmarks that are there are more or less kind of corrupted. So, you know, they never reflect what the true performance of the system is. So the best measure is actually you take your own problems that you don't know the answers to and try them. And then you find that, actually for years and years in the early 2000s, the best SAT solvers are some guy's master's thesis. It was a SAT solver called Siege. I mean, it was hands down the best SAT solver, except it never won the competition. so it just reflects how people have gamed the. I mean, they not only gamed the competition, they gamed the input to the benchmarks as well. So the SMT lib has just got so much garbage in it that it's not really a very good reflection of how well the thing will actually work for your problem. So that's something that I suspect other communities have probably better ways of doing the benchmarks.
I mean, so it's one of the goals of Judgment Day, which is partly generated from problems we have in Isabelle.
That's right, yeah. So natural problems are much better representative of things you run into, for instance. So, we won't have one next week, but we'll have one maybe the week after that. So Monday after the workshop, we'll have the next session. Thank you, everyone. Let's see if I've learned how to.
Is this done on your home page or
The other one?
So I have been putting the slides out there. By the way, all of you should put slides. You can go to your My Seminars and put slides in there. All of you should put your slides in there. But I asked the IT guy, and he says I'll look into it. Why haven't the slides shown up? So, like my talk from last week, the slides should have been there. I mean, including the other talks also. They've all put their slides there. But they just haven't shown up yet.
all right.
And don't forget, tomorrow Johannes will be talking again.
Okay.